Hello, 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 hello. Welcome back. Am I audible and visible to all of you? Let me know in the chat box. Aspirant, hello beta. Asana, hello beta. Okay, so that means my voice and my video is very clear to all of you, right? So in yesterday's class, we had the discussion on some parameters like the superposition principle, how to find the net resultant force on any body, and we done a lot of numericals from PYQs of NEET and JE as well, and we done some amazing numericals from very great books of physics, right? Hello, beta. So yeah, so in this particular lecture, that is today lecture, it will be a short lecture, not that much, right? Yesterday we had the lecture for 2 hours almost. So in this particular lecture, we will be discussing equilibrium and numericals based on this particular thing, then SHM numericals. Okay, let's start now. One second. There is some lag. I need to check it out. So in last class, what we discussed, no, beta? I guess this was the last numerical that we had the discussion on how to find the time period of any particle revolving in a circular orbit of a particle placed at the center. So this was the numerical last time we discussed. So now today's class we will starting from this particular numerical, and this one is very good one. And this numerical basically designed to just revise your concept of if you are having two bodies and you are touching two bodies, not a conduction part. If you have present in the last lecture, so we had discussed the conduction part. If we have two bodies with the same radii and we are just touching them, what will happen to their total charge? Or if the radiuses are different, then r1 by r1 by r2, right? Then total charge. If there is a sigma is given, so how we can do these things? Okay. So let us just numerical. I will just read the numerical firstly, then we can do it. Okay. So the numerical is like we have two spherical conductors. What we have? Two spherical conductors. So I will just make here conductor, one conductor, and you can see the name of first conductor is given by B. No, yeah, it is name is B, conductor B, and let us suppose the radius of this B is given to be R. Suppose we have one more conductor. We have one more conductor. Once again, yeah, we have one more conductor. So I will just make here one more conductor. So if we talk about this one, similarly, this is C with the radius R. You can see here, no? In this numerical, it is given us that two spherical conductors B and C both have equal radii. Means the radius of both B and C equals, carrying equal charge. That means if we talk about the charges, B possesses charge some, let us suppose Q. Same way the C is having charge Q. Okay, then in them repel each other with a force when kept apart at some distance. Let us suppose the distance between them is given by r, small r, and they are facing a force F. They are facing a force F, okay, as per the conditions. Now the second condition is a third spherical having same radii as that of B but uncharged. So we have one more sphere here. Okay, what we have? We have one more sphere here. I will just write here one more sphere here. And the radius of this sphere is how much? Same r, but it is neutral. That is charge is zero. Charge is zero. Okay. What is the condition now? Now this new body. Let's suppose this body is A. Now this body A is brought in contact with C, then removed away from both. No, then but uncharged is brought in contact with B, C, then removed away from both, and new force of repulsion between B and C. Between B and C. But I guess there is some sort of error in the numerical part. So I will just give you some way how to solve it now. So firstly, what we have here. So look, I will write here. Okay, look what I can write here. So 1 second. Okay, look now. So numerical is like that. What we are doing, firstly, I am taking the A body, and I am touching it with the B. First part. Second part, then after touching B, then I am touching it with the C. Second part. Then we have to find out charge between B and C. At the end, between what will be the electric force between B and C. Initially, between B and C, my force is F, right? According to the first condition, what we are doing, beta? We are taking, look, we are taking here B. This one is my B with radius R, charge Q. This is my B. And I am touching it with what? With A. Radius R, A. Charge is 0 initially. Now what will happen now? There will be a charge distribution. Look, if we have identical charges, identical spheres, so there will be a half of charge. So now my final charge will be Q by 2. Here it will be Q by 2. Done. So now my body B is here. It is radius is R, charge B. Now the final charge on B body is Q by 2. I am taking now this A and touching it with the C. Now here I have now body A with radius R. It carries charge Q by 2. Now I am touching it with what? Body C with same radius R. It contains charge Q. What will happen to new charges? Sir, new charge will be the half between these two. So I can write, sir, it will be Q by 2 plus 2 half. So it would be Q by 2 plus Q by half. It would be 2Q plus 1, 3Q, 3Q by 4. So final charge will be 3Q by 4 and 3Q by 4 by conduction part. Now I have here what, beta? I have here C with radius R, charge is 3Q by 4. Now radius, the distance between them is same R. We had to find now the force between these two. Force between these two, okay? So what will be force? I can write force is equals to K. Q1 is Q by 2. Q2 is 3Q by 4 whole divided by R square. So look, 4 to the 8. Can I write here? It would be 3 by 8 K Q square by R square. This is the previous force. So I can write my new force is equals to 3 by 8 times my old force. So this is my answer, and this is how we can do it. Okay. So it is 3 by 8 now. Yeah, 3 by 8. That means option force is correct. So that's why we are saying that conduction part is important for you. If you are studying anything now, if you're studying conduction, friction, or induction, those are very important for you. Why? Because in this particular numerical, we have to apply the formula for the conduction part only. Okay. So we had complete the force between multiple charges. Now let us study about equilibrium. Let us study about equilibrium. Okay. Equilibrium means where my force F net would be zero. Simple, na? Equilibrium simply means it is a particular point. If we talk about the equilibrium point, it is that particular point where the summation of all the forces is equal to zero. Clear? It is that particular point where summation of all the forces at that particular point is equal to zero. So at that particular point, we will call it a what? Equilibrium position. Look now, how to deal with equilibrium. Let us suppose I have a charge. Suppose now I have a charge here plus Q. Suppose plus Q. Our distance part, we have one more charge plus Q. I will ask you a question, beta. Where I need to put a charge Q so that it doesn't feel any force. So that it doesn't feel any force. That means find the equilibrium position in this particular numerical. Let us suppose, let us try. Let us suppose I am taking this Q and I am putting it here. It is Q, now it is positive. What will happen? Look now, what will happen? This Q charge will repel it. So it will just apply force on it like this, F1. Okay, look, this is also positive. This will also apply force on this one in this way. That's F2. So look, F1 and F2 is in the same direction. So there is no chance that they will cancel out their effect. So my net force will be like this. My net force is like this. So my particle will feel a force in my leftward direction. તો તગડો ભલાયો છે. So it will feel a force. Now it will feel a net force in leftward direction. So that here my force is not equal to zero. So this shows that at this particular position left of the Q, there won't be any position where my F net is zero. So no equilibrium in the left side. Now let us talk about the right side. So let us suppose second condition, first condition or first point, second point. Now what if I will place the Q charge here? Q charge here. Look, this positive will repel it like this. Same, it will apply some force. Let us suppose F1. This is positive. This one is also positive. Positive repels. It will have a force F2. So my F net would be in this way. My F net is in this particular way. So look, F net won't be equal to zero. So yes, right side, no equilibrium present. Now there is a third condition. Let us suppose I am just putting my charge between these two here. What will happen here? Now look, this positive will repel this positive in this way, F1. This positive will repel this positive in this way. Look, F1 and F2 both are opposite to each other if magnitude of F1 is equal to magnitude of F2, so my F net is equal to 0 now. My F net is 0. If F net is 0, yes, it is at the equilibrium position. So what you need to learn from this particular point that yes, if we have same polarity charges, positive positive or negative negative. The equilibrium position will be always between them. If we have same polarity, no? If we have same polarity charges, the equilibrium position will be in between. In between. First point. Now let us take one more example. Look, if this is my plus q, this one is my plus q, and here what we have minus q. Plus q and minus q. Look now. Same, we have one more charge, test charge q. Now due to this test charge q, I need to find out the equilibrium position for it. Let us suppose I am just taking this here. I am just taking here, right? Look, positive, positive, sir, it will repel like this, F1. Negative, positive attraction, it will have like this, F2. Therefore, in between, my F net is not equal to 0. I will take here, now look, Q is here. Negative, positive attraction like this. Positive, negative, positive, positive repulsion like this. So yes, if my F1 is equal to F2, so I can write, sir, my net force at this particular point is 0. Yes, this is possibility of my equilibrium position. Now, if I just place this charge here, okay, Q. Look, positive, positive repulsion, it will go in this way, F1. Negative, positive attraction, it will go like this way. Look, opposite, F2. If here also, if F1 is equal to F2, so yes, sir, I can write F net is equal to 0. Yes. So if we have same polarity, so my net point, this equilibrium position is always in between. If we have different polarity, so it will be the outside of these two charges. Okay. Look now. Look. This was some points related to equilibrium. Now here, now look. First point. If we have same nature charges, then my equilibrium will be the in between. If we have opposite polarity charges, then it will be the outside. And always my equilibrium will be always closer to the smaller magnitude. Okay, it will be closer to the smaller magnitude one. Done. Look here, you will see two numericals here. No? Look. First numerical is this one. First numerical. Look here. We have two charges. We have plus q, 4q, we have plus q. So we need to just think about these points. Sir, if same nature, yes, this is same nature charge. So equilibrium will be always in between. Equilibrium will be always in between. One second. Equilibrium will be always in between. Now my third point is it will be always closer to the smaller magnitude one. Look, this one is q only, this one is 4q. I guess this is smaller one, so it will be closer to what? Smaller one. So I can place his q. I will place here what? Q. Look now. If the whole distance is given be r, so I guess, look, so this distance is how much? Let's suppose x. If this is x, so how much this one is? Sir, I can write the whole r minus x. R minus x, right? Okay. So the condition is my net force on this particular charge should be 0. So how many charges are acting on it? Sir, I can see here if this is positive, this is positive. So there will be my force 1. Force 1. Done? Sir, this is positive. So there will be what? Beta force 2. So if we assume that at this particular point, it is an equilibrium. So my both forces magnitude should be equal to plus 0. Or I can write, sir, my F1 should be equals to F2. By Coulomb's law, F1 is equals to, is it K? Yes, sir. Q. What is Q? Sir, it is Q, this one Q. It is Q2 is Q whole divided by distance between them. It is X, so I can write X square is equals to, what is F2? So this F2, K, Q, this Q, sir Q. Q2 is 4Q, I can write 4Q whole divided by the distance between them, that is R minus X whole square. R minus X whole square. Look here, sir, K cancel out, Q cancel out, this Q cancel out. So what I can write now, look, it is 1 divided by X square is equals to 4 divided by R minus X whole square. I can do one thing. I will take it here. Now look, it would be R minus X whole square divided by X square is equals to 4. Look how we can manipulate now. Look, I can write R minus X whole divided by X. I will place 2 here. Square now to both the terms is equals to 4. I can write R minus X divided by X equals to root 4. I guess root 4 is 2 only. So I can write R minus X is equals to 2X. So R is equals to 2X plus X. So R equals to 3X. Therefore, my X came out to be R by 3. It is how much? R by 3. That simply indicates, sir, if we'll go R by 3 distance in left side towards my smaller charge, we will find a point where the F net is 0, which will be at the equilibrium point. This is how we will find the equilibrium position. And always remember one thing, that we need to measure the distance from the smaller one only. We need to measure distance from the smaller one only. Okay. Look, in the same way we have next numerical. This one, no? This one. Look here. Minus 4Q is big or Q? Sir, minus 4Q. Okay. That's why different polarity. So my charge will be outside. It will be closer to the smaller one. So I guess Q is smaller one. So yeah, it will be closer to this one. So let us suppose the distance of the equilibrium point from the plus Q is X. That means this distance would be equal to how much? Sir, R plus X. Look, forces. Plus like charges repel. So sir, my F1 will be in this way. Minus plus attraction, sir, my F2 will be in this way. So if at this particular point it is equilibrium, so that simply indicates my F1 should be equals to F2. I guess F1 is equals to Q1 is Q, Q2 is Q whole divided by my X square is equals to F2 is K, it is Q, then 4Q whole divided by R plus X whole square. K cancel out, Q cancel out, small q cancel out. So I will get 1 divided by X square is equals to 4 divided by R plus X whole square. Done. So in the same way, what I can write R plus X by X whole square is equals to 2 square. Cancel out. One more way. So R plus X came out to be 2X. 2X. So R is equals to 2X minus X. So R equals to X only. So my R came out to be X. Okay. So the distance of the equilibrium point from the smaller charge is how much? Sir, R. And if you need to calculate from the bigger one, this one, sir, it would be how much? This one, now from this one, sir, it would be R plus X, which came out to be 2R. This is how we can manipulate our numericals. This is how we can manipulate our numericals. Done? Now, like next numerical. Is there next numerical? One second. Okay. Now this one is interesting. Now this one you can write also. This one is also important, or this one is interesting case. Look, look, beta. We have two charges with opposite polarity. So if we have two charges with opposite polarity and we want to find out where the equilibrium position would be, either it would be on the left side or in between, okay, or the right side. The condition should be, if we have same polarity, so the equilibrium will be the in between. If we have opposite polarity, so it would be the outside. Now here the question is, sir, we have minus 4q and plus 4q. That means we have opposite polarity. We have opposite polarity. So which simply indicates that my equilibrium point should be outside, either left side or right side. And it would be closer to the minimum charge one. Look here, sir, but we have same charge. Now look, minus 4q plus 4q. Minus 4q plus 4q. So same magnitude but opposite sign. So the solution for this one, what? Sir, no equilibrium possible. For this one, no equilibrium possible, or you can say, sir, exist at infinite. Okay, sir, no equilibrium possible, or you can say, sir, it exists at the infinite. Look, if my charge particle, so it is here now. So look, it is closer to the 4q but away from minus 4q. So there is no chance that F net is equal to 0. No chance. And the same way here, no chance. Here, no chance. Okay. Now one special case also. Now if we have the same polarity, now before that we were having opposite polarity. But if we have no same polarity with same magnitude, yeah, this one is possible. So let us, in the same way, let us place a charged particle here. Let us take it closer to this one now. Let's suppose, or this one, there is no issue. If this distance I am taking it x, so this one would be r minus x. So here, if we are assuming it as a equilibrium, so F net is 0 here. So if F net is 0, look, positive ripple, so it would be F1 here. Positive ripple, so my F2 would be in this direction, F2. So can I write now, sir, F1 is equals to F2? What is F1, sir? It would be K QQ whole divided by X square. K2 would be, sir, K QQ whole divided by R minus X square. Look, K cancel out, Q cancel out, Q cancel out. So what I have now, 1 by X square is equals to 1 divided by R minus X whole square. Now take inverse of these two, what I will get? X square is equals to R minus X square. Cancel out. So I am having here X is equals to R minus X. So I will have 2x is equals to R. So my X came out to be R by 2. So it will be the middle of these two. It will be at the middle point of these two. So if we have opposite polarity, but same magnitude, so no equilibrium possible. But if we have same polarity and equal magnitude, yes, in between the equilibrium is possible, but it will be at the same middle point. No, it will be at the middle point. Okay, now next numerical is here. Okay, now let us do one numerical. Let us do one numerical. So in my equilibrium, now we have two types of equilibrium. What we have? Two types of equilibrium. You will find two types of meaning of questions. Why are the equilibrium would be? That means my particle equilibrium. But you will find the particle's equilibrium position. So particle equilibrium. Particle equilibrium. Second term, you will find if the whole system is at equilibrium. Is my whole system is at equilibrium. So you will find what? System equilibrium. System equilibrium. Okay. So in numericals, you will find these words: particle equilibrium or system equilibrium. Particle equilibrium means my net force on that particular particle is zero. Particular, my spelling is not good. My F net would be zero for a particle. For system particle, so F net for system will be zero. Force net on system would be zero. How to find it now? So in this profile, you need to find what? Distance of equilibrium. Distance. If we will get anything now, but you need to find out the equilibrium position. So you can use the particle equilibrium concept. If you need to find, there will be a question now. If the whole system is in equilibrium, find the magnitude of charge. Find the magnitude of charge. So this one came under the profile of what? System equilibrium. Okay. The numericals that we were doing now, the previous one, these these 2-3 numericals. In these numericals, I guess we find the distance now. If we find the distance, these belongs to what? Particle equilibrium. If you are finding the distance of your equilibrium, so it comes under the criteria of what? This one, particle. Now for system equilibrium, now how we need to manipulate and how we need to do these things, right? Look. Suppose I will take this numerical only. Now this one, I will take this numerical only. That is, look it up. That is, if I have a system like this, look. If I have a system like this, look it up. Here. This is plus Q. Distance is R. Distance is R. So if the distances are, first point, find position on equilibrium. Find position of equilibrium. Second, find value of charge so that the whole system will be in equilibrium. Suppose I am taking, sir, both charges are positive, so equilibrium will be in between somewhere. Now I will write here. That's why my Q is here. My Q is here. So this would be my X from this particular side. It would be X, and this would be how much? Sir, R minus X. And we just now concluded it that, sir, my X will be equals to R by 2. Okay, that means we have to place it in between the two charges, right? So here I will get my what? Equilibrium. Okay, if instead of this Q now, if we have any charge, 4Q, 10Q, 100Q, always and always my equilibrium will be here. But if I am placing any charge here, so what should be the value of this charge? So my whole system will be in equilibrium. Done. So for this second one, now how we need to look? For first one, we have to make a equation between these two and between these two. But for the second one, I have to make an equation between these two and these two. Okay. If this particle needs to be in equilibrium, that means, sir, if this particle, look, I'm just doing this one. If this particle should be in equilibrium, that means my force net here should be 0, or force net on this should be 0, or net force on this would be 0 for second condition. Now I am taking this one. Now look, sir, let us suppose this is positive. This positive will repel this positive. So I guess force is F1 here. Suppose now this is positive, this is positive. My F2 is here. So look, there we have two forces, F1 and F2. If it needs to be in equilibrium, so F net is 0. So can I write now, sir, F1 plus F2 both needs to be 0? Yes. So which indicates my, sir, my one force should be equal to my second force. Okay, sir. What is F1? F1 is between this one and this one. Suppose. So it is K, Q, Q by whole distance. Now it is R. So I can write R square is equal to F2 is between these two. So minus K, Q, Q whole divided by R by 2 whole square. Look, 1Q cancel out. 1K cancel out. So what I can write, sir, it came out to be, sir, Q divided by R square is equals to minus Q whole divided by R square by 4. So I can write, sir, it would be Q by R square is equals to minus 4Q whole divided by R square. R square cancel out. So you can get, sir, Q should be equals to minus Q by 4. Minus Q by 4. So it simply indicates, look, it simply indicates one thing here, that is, sir, if the whole system should be in equilibrium, so the value of this charge would be equal to minus Q by 4. So we now know 2 points, that if you need to find the position of the equilibrium, so how we can do it? If you need to find the magnitude of the charge, so the whole system will be in equilibrium, how we can do it? How we can do it? Let us do a NEET PYQ, and it is also important for your examination. Look, suppose we have a square. We have a square like this. Look, if we have a square like this, okay, and on the each corners we have some charge. On the some each corners we have some charges. We have some charge. Done. Look, here we have Q. At this point I have Q. This side Q. This side Q. We know that there is no possibility that this system could be in equilibrium. Let us place a one charge here, Q. Q. We don't know the magnitude of Q. We know that it is at a center point. One thing we know it now, but we doesn't know that what is magnitude of it. Why, sir, it is at center? So first of all, if you want to study, if you want to get equilibrium point, so it should be at that particular point where my F net is 0. For any regular polygon, it is at the center. I guess in yesterday's class we had done this concept now. Yes. Look. So look what will happen. Look what will happen. This plus Q, so there will be what? There will be a repulsion. There will be a repulsion. So like this. It would be F1. Suppose F1, and F1 is equals to, sir, K. Q1 is Q, Q2 is Q whole divided by, so it is X. X square. This Q repulsion, it would be like this. Sir, F2. It is how much? Sir, K, Q, Q by X square. So my answer came out to be K, Q square by X square. This is also how much? Sir, K, Q square by X square. Look, both are equal. Both are equal. So it is net value would be how much? It is net value would be, we had discussed it now. It is net value would be 2f cos theta by 2. So angle between them is 90. So can I write it like 2f? F is equals to k q square by x square cos 90 by 2, that is cos 45. I can write 2 k q square by x square cos 45, and cos 45 is how much? Root 2. I can write 2 k q square by x square into 1 by root 2. 2 into root 2 is root 2. So I can write root 2 k q square by x square. So the net is in this way. It is my f net. It is how much? Under root 2 k q square by x square. Look, if you are finding net now, so there is no usage of these two now. No usage of these two now. No usage of these two now. Okay. Now there is one more force now. This q. This q. Look, if this is x, this one is x. So this one is a hypotenuse of side. It would be how much? Root 2 times x. Positive, positive, ripple. So this would be in this way. Yes, sir. How much? Let's suppose it is f dash. It would be k q q whole divided by under root 2 x whole square. So it would be k q square divided by 2x square. Now both this one and this one both are in same direction. So to get the net of these two, I will write k q square by 2x square plus under root 2 k q square by x square. So my net force acting on this one is this much. Okay, one more force. There is one more force. Do you know the force is? This one. Okay, look, if the whole, now look, if this is my, like this, if the whole length of this one is under root 2x, I guess I need to half it. So the half length would be, under root 2x whole divided by 2. Here is q, this one is q. Now, I guess one more force is there, this much. It would be k, q, q whole divided by under root 2x by 2 ka whole square. It is equals to k, q, q whole divided by 2x square into 4. One more force. So at the end, how much force we have? Look, I need to just rub all these things now. Look, why? Because we got it now. Look, there's no need of writing this one also. Okay, no need of this one also. No, this one also. Look. So if we want the equilibrium, so on this particular charge, we have the net force in this way. Let's suppose it is F1 and F2. F1 is the whole one. It would be equal to how much? K q square by 2x square plus root 2 times k q square by x square. This one second. Second one, my F2 is equals to KQQ whole divided by 2x square into 4. 2 1 2, 2 2 are 4. So it would be how much? 2KQQ by x square. Look now. If the system should be in equilibrium, if the whole system is equilibrium, that simply indicates the summation of the net force should be 0. So can I write here now? Beta? What beta? Can I write here now that it is k q square by 2x square plus under root 2 k q square whole divided by x square plus 2 k q q whole divided by x square is 0. Yes, sir. Look, x square, I will take it common and cancel out. K common and cancel out. This q, 1q cancel out. So what I will get here? I will get q by 2 plus root 2 times q plus 2q is equal to 0. Okay. So can I write here, sir, my 2q is equals to minus q by 2 plus root 2q. So my, I can write 2q is equals to minus q plus 2 root 2 times q whole divided by 2. Whole divided by 2. Look here. So I can write q came out to be, I will take q common. So it would be minus q 1 plus 2 root 2, then 2 to the 4. Yeah. So this should be the value of my q. This should be my value of this q if I need this particular question to be at the stable equilibrium system. So for particles, it is a center. For system, the value of the central charge would be this much. Okay, this is how we can do it now. Okay, I guess you don't have any doubts about this one, no? Okay, clear, Udo? Okay. Now look, we have now one more concept known as SHM concept, simple harmonic motion. This chapter was in 11th standard, but it is application you can see here also. Okay. So what basically you have to learn from SHM. Okay. If your particle is observed this equation that if my force is equals to minus k x to power 1, this particular motion is known as SHM motion. Okay. Do you know why? Look, if we have something like this now, my particle is here now, look, and I am displacing it now, look, it would be here sometime, right? Look, so it will, now I am just taking off my what, my force. So it is restoring force will be like this, my restoring force. That means you are displacing it in this way, but restoring force is opposite. That's why it is minus kx. Okay, f and x, it is opposite to each other. You are taking it like this, displacement is going like that, the restoring force is backwards. Okay, if we have some bowl like this now, look, if we have some bowl like this now, beta, bowl like this. Okay, so what will happen now, beta? It will go here, then it will come back, but it will not stop here due to its potential energy. It will go upwards here. Okay, but there will be a point now where it will come to its mean position. It is a mean position. This is a mean position. It will come back to the mean position. If your particle comes back to the mean position, okay, so this particular equilibrium is known as stable equilibrium. This particular equilibrium is known as stable equilibrium. Okay, I will just make here a note, one short note. Look, simple, look, very famous sort of figure. Look, one particle I'm here, one particle here, and one particle here. And you are applying force. Now, if you are applying force here, so definitely it will come back to the position. So if your particle comes back to the position, so this is the example of a stable equilibrium. Stable equilibrium. Look, if you are displacing it now, there is no chance that it will come back to the position. This is unstable equilibrium. This is what? Unstable equilibrium. But look, if you are displacing it, you are applying force up to this particular point that you are just taking off your this force now. So it will be up to the particular position only. So this one is known as what? Neutral equilibrium. Displacement is as long as you are applying force. It is neutral equilibrium. Okay, this one is not important. These two are important in our cases. Done now. So these are some cases in my equilibrium. Look, something I will just tell you in SHM, the basic of SHM. Then we can just move to the next topic and do numericals. In 10 minutes, we will just clear the whole thing, right? Look, my F is equals to m in F minus kx. What is F? By second law, it is mass into acceleration, so it is m into a equals to minus k into x. What is A now? Sir, A is minus K by M into X. We know one equation from my equation, that is A is equals to minus omega square X. Look, A is A, X is X, but here you can say these two terms should be same. Okay, that means my omega square should be equals to K by M, and omega is how much? Under root of K by M. Do you know what is time period? Sir, time period is equals to 2 pi by omega. 2 pi. What is omega now? Under root of K by M. Now take out upside. So my T would be equals to 2 pi under root of M by K. This is one more formula to get my time period. Okay. One more formula to get my time period. Done? Is there any numerical here? Okay. So let us do 1, 2 numerical. Then we can just clear our session. Okay. Look. Okay. If we have charges like this, look. 1 second. One point here plus Q. 1 point here plus Q. 1 point here plus Q. So if the distance is between the origin, it is origin, no? This one is A, this one is A. Add some distance here. Y distance upwards, we have a particle, let's suppose Q naught. Then we take off the forces. Can you just tell me if this is positive one? First case, if it is a positive one plus Q naught, so find is it a stable equilibrium or unstable equilibrium. Second case, if it is minus Q naught, then tell me is it a stable equilibrium or unstable equilibrium. How we can do it? Look beta. This positive and positive ripples in the first case, it will apply a force F1 here. Suppose. In the same way, these are two positives. Now, these are two positives. This will repel like this, F2. This is theta. This one is theta. Suppose, now, look. This one would be theta. This one would be theta. It would be here what? Sir, F1 cos theta. It would be F2 cos theta. One component here, sir, it would be F1 sine theta, or one more F2 sine theta. Look, F1, F2 same magnitude, cos theta same. So these two will get cancelled out. So my net force will be upwards. So it would be 2F sine theta. So every time now, if you are doing this thing, so your particle will go upwards always. So it will not come back to the original position. It will not come back to the original position. So I guess it is a case of unstable equilibrium. It is a simple case of what? Sir, it is a simple case of unstable equilibrium. Now, in my second case, look. In my second case, if at this particular point I have plus Q same, here I have plus Q. Origin 0, A. Now upwards here at Y, I have a charged particle minus Q naught. What will happen? This Q will attract it by force F. This Q will attract it by force F. Net force will be downwards. So look, the force will be towards the origin. Force it towards the origin. That means the particle will be at origin. So this is a simple case of what? Stable equilibrium. Simple case of what? Stable equilibrium. Clear? Clear, beta? Simple case of stable equilibrium. Okay. This was the axial. This was the equatorial position. Let us talk about the axial one. Okay. How, sir? Look. it is like this. Okay, here I have a charge plus q. I have a charge plus q. In between, I will place a charge somewhere here, plus q naught or minus q naught, no issue. I will fully place plus q naught. Okay, first case. What will happen? This F will apply a force F here if the distance is r by 2, r by 2. This Q will apply force F here same. Look, if we are displacing it, look, if we are displacing it by x distance, so this particle will be closer to this one, so this will apply more force. If more force, so this will be more. In this case, my F1 will be more. So it will try, look, my x is going in this way, but my net force is in this way. So it will come back to the original position. It will come back now to the original position. Look, this we are taking the plus q charge in this way, so it is getting closer to this one, so the force applying by this one will be more. So yes, F1 is more, so it will try to just bring it to the original position. So it is a simple case of what? Stable equilibrium. One more example for -1 now. Look, now here it is plus q, then here let us suppose at center it is minus q. What will happen now? Sir, at initial it is r by 2 and r by 2. This q, this minus q, attraction here, sir, F1. Suppose plus q minus q attraction here, F2. It is at what? At equilibrium. Now I am displacing the charge towards this. I am displacing it here now by x. Now this charged particle will be closer to this one. So my F2 is more, my F1 is less. So my F2 will be more than F1. So you are displacing here and my force is more than here, right? So my net force will be here. So look, displacement direction and this direction is same. So it won't come back to the original position. It is unstable. It is what? Unstable position. It is what? Unstable position, right? Clear? Now let us do 1, 2 numericals, then we can just, then we had the completion of our topic. Okay, let us do one last numerical. One last numerical. Okay, last and a good numerical. Okay, and hard type, hard one. Good numerical, last one. If you have any doubt regarding this particular chapter now, this particular thing now, right? In the next class, we will be starting electric field now. Okay, let's do a numerical. So we have two charges here. Look, plus q, plus q. Okay, two charges. So if in the two charges we are having a one small charge q, one small charge plus q here with mass m. If the distance between these two are a, it is at the central point here, right? Central point. Now what we are doing now, we are displacing it. Let us suppose I am displacing the charged particle from this particular position to this particular position. This is x distance, x. Now my particle would be here q. So look, this distance now is how much? Sir, it is a minus x. Now this distance would be how much? Sir, a plus x. What will happen? Now what will happen? Sir, this particle will apply more force onto it and this will apply low. So my net force will be in this way. Now the particle will not stop here. It will go up to this particular point. Now at this particular point, this particle's force will be maximum. So in this way, my particle will do some oscillation. In this way, my particle will do some oscillation. Look, my particle is here. Okay, this particular hand is applying some force. If I am just displacing it in this way, so this will apply more force. So my particle will go like this. Here I have one more particle. It will apply force now. So my particle will do oscillation or SHM about its mean position. So we need to find out the time period of this particular oscillation. So how to find the time period of this particular oscillation? How we can do it? No, it's a very good numerical. So I guess I need to check out firstly. Is there any doubts that you're having? Look 1 second. 1 second. This is last numerical. Then we can just stop our class. Okay. Am I audible and visible? Okay. I guess I am now. Okay. Look now. So when my particle is at this particular position, when my particle is here, so look, this one is F1, this one is F2. F1 is due to this particular particle and F2 is due to this one. So my F net would be in this way. So I can write F net is F1 minus F2. My F net is F1 minus F2. 1 second, beta. My audible, 1 second. Whatever is good, everything good. Yes. So what I can write now, look, my F net equals to F1 minus F2. What is my F1? K, this Q divided by this distance. It is A minus X square minus K, this Q square whole divided by this distance A plus X whole square. Okay. 1 second, beta ji. Okay. So look what we can do right now. Can I take common something here? Okay. I will take K, Q common. Then what we have here? So 1 divided by A minus X square minus 1 divided by A plus X square. Okay, it is K, Q. Now I will take here cross multiplication. Now look, 1 into this multiplication into this multiplication and this multiplication. Look, can I write here that it would be A plus X square, then minus A minus X whole square whole divided by, so it will be A minus X square, then A plus X square. Look, A plus X square, A plus B का whole square. It would be A plus B whole square. And right here, K, Q. A plus B whole square, so it will be A square plus B square plus 2 times AB minus A minus B whole square, A square plus B square minus 2 AB whole divided by A minus B square, A plus B square. It will be A square minus B square. Done. And then whole square. Look now. KQQ. Why my video is not opening? 1 second, beta. There is some issue with it. 1 second. Okay. I guess I am visible and audible, no? Is there anyone who can just tell me if I'm audible or not? Huh? It doesn't get open now. That's why I was telling you. Yes, no? I am. So what I can write? No, look, it's A square plus X square plus 2AB. Now minus A square. Sorry, it is not minus AB. It is A it is a, it is not b, na, it is x here. 2ax minus a square minus x square plus 2ax whole divided by here a square minus x square का whole square. Look, a square cancel out, x square cancel out. It is 2ax, 2x, it is 4ax. I can write that k q q 4ax whole divided by a square minus x square का whole square. One thing that you need to notice na, the displacement of x na, it is very small to as compared to the distance between these two. Okay, so what I can write from here na, look, it is k q q, then I can write 4ax then whole divided by, look, a square minus x square is approximately equals to a square only. So I can write, look, a square whole square. Done. Look now, k q q, then 4ax whole divided by a to the power 4. 1a cancel out. So my net force came out to be k q q. Then we have 4x whole divided by a to power 3. It is 1 second, one second. CB. I think we had done some mistake here now. 1 second. No, we are correct. Okay. Done. So look now. Let us compare the whole equation to what? To f equals to kx. Look, x same. Then can I write my k came out to be 4kq q whole divided by aq? Yes, sir. This is my k. This is my k. So can I write now my time period? Is this 2 equals to 2 pi under root of m by k? 2 pi under root of m. M is m. What is k? Sir, k is equals to 4kq cube by a cube. This is the time period of this oscillation or SHM. Okay. Done. So by this particular numerical, we had completed Coulomb's law part. Now from tomorrow, I guess tomorrow or on Monday, we will start electric field. We'll start electric field. If you have any concern, you can ask me now. If not now, then you can ask me in the Telegram group also, okay? Yesterday we had a long class now. That's why I need to just shortcut to this class. And thank you once again. Thank you very much, and bye from my side. Bye. Thank you, Thank you very much. Thank you. Bye. Good night. Good night.